Hello, this is a video about momentum and impulse. Let's get started. Alright, so here's the goals for the lesson. After this lesson, you should be able to define what momentum is, define what impulse is, determine the differences between elastic and inelastic collisions, and use momentum and impulse equations to calculate velocities, masses, and forces. So, what exactly is momentum? Well, think back to Newton's first law. Newton's first law says that things in motion want to stay in motion and things at rest want to stay at rest. Well, momentum is really that concept. It's really that things that are moving, they want to continue moving until acted on by a net force. They have momentum. An object's momentum can also be found by taking the object's mass times its velocity. If you have something that's really heavy, like a semi, it's going to have more momentum than something really small like a cat. If a semi is moving really fast, it's going to have a lot of momentum versus if it's moving slower. So think about, another way to think of it is how much force would it take to stop that semi? If it's moving pretty fast, it would take a lot of force to stop the semi. If it's not moving very fast, it's not going to take as much force to stop that semi. And thus, if it's a fully loaded semi versus an empty semi, it would take less force for empty semi. So momentum is really an object's mass times velocity, but it's that concept. Impulse, then, is a change in momentum. So if something changes its momentum, whether it changes its speed, it goes faster or slower, or it changes its mass. Let's say you had a rocket that was traveling through space and it deposited a good chunk of its mass to space. Its velocity would increase because its momentum would be conserved. So we'll talk more about that when we talk about conservation of momentum. But this video is just about the concepts of momentum and impulse. But anyway, let's get rolling. Elastic collisions. We talked about there's two different types of collisions. One is an elastic collision, the other one is inelastic. All right, so an elastic collision is when there's a transfer of momentum and there's no loss of kinetic energy. And I'm going to use a simulation to kind of represent that for you guys and gals. But there's no loss of kinetic energy. So the objects basically bounce off of each other. This collision is called elastic. Inelastic collisions then have some sort of loss of kinetic energy, meaning that energy goes into sound, friction, it goes into forming the two materials. So let's say you had a car colliding with another car and the two cars smashed together. Well, a lot of that energy went into smashing the two cars together. And so these types of collisions, they usually stick together. Let's stick together, yeah. Now, think about two cars that collide and they stick together afterwards. So a perfectly inelastic collision is where they stick together. A perfectly elastic collision is where they bounce off each other. So let's do a little simulation here. And this is FET, Colorado. They have some good simulations with different things. And here's, let's do the different situations that we talked about. So let's say we had a red ball here with a mass of 1 kilogram. And it's going to move to the right here at 1 meter per second. Over here we have a green ball. It's just going to remain stationary. Now the symbol for momentum is a lowercase p. This ball's momentum is 1 for its mass times 1 for its velocity. So 1 times 1 is 1. Its momentum is 1 kilogram meters per second. It's kilogram for mass, meters per second. That's the unit for momentum. And then this ball has 0 momentum because it's not moving. Even though it has mass, it's not moving, so it has no momentum. I want to hit play, and what's going to happen is this ball is going to move and collide with this ball. This is a perfectly elastic collision. If we remember that elastic collision means that no loss of kinetic energy. So let's see what happens. Boom. So I'm going to pause that. If you notice, this ball was moving to the right at 1 meter per second, and it collided with this ball, and now this ball is stationary, and it transferred all of its momentum over to this ball. I want to reset this. What if they were different sizes? What if this ball was smaller and this ball was bigger? Any predictions? Let's show the values here. This ball's velocity is 1. This ball's velocity is 0. This ball's velocity, or mass, is 0.5, so its momentum is 0.5 times 1. So think about the momentum before. The total momentum before the collision is 0.5. After the collision, it all should be 0.5. But if it's elastic, what should happen? This ball should transfer all of its momentum over to this ball. Boom. Oh, look at that. This ball has a momentum of negative 0.25. Negative because it's going backwards. This one is positive 0.75. And the total momentum, if you notice, is will be 0.75 minus 0.25 is still 0.5. Okay. Let's try a inelastic collision. Let's see what happens. So we can both the same size. Keep it simple. We'll try an inelastic collision. Okay. And we'll hit play and we'll see what happens. Show values once again. We got 0.5. This was not moving. Hit play. Now they stick together. And notice that they're both moving at 0.5. I'm going to move this away. This one's moving at 0.5. This one's moving at 0.5. Before it was moving 1, and now it's moving 0.5. So now let's go back to, let's try inelastic this case. Hit play. Boom, they stick together. Notice how this one slowed down, and this one, well, it's not traveling the same speed as this one because they're stuck together. So that's an inelastic collision. So let's go back to our definitions here. Remember that, do present here. So an elastic collision is when a collision between two more objects where there's a transfer of momentum, there's no loss of kinetic energy, and they bounce off of each other. That was like that first example where they bounced off of each other. An inelastic collision has some sort of loss of kinetic energy. We didn't hear any sound or anything, but some of that energy must have went into forming those two spheres or sound or whatever, and these objects stuck together. So try to think back what the differences were between those two. All right. So there's an equation for each one that you can figure out what happens. So an elastic collision, if you take the object's mass, let's say this is object 1, the red ball. If you take its mass times its velocity, so m1, meaning that object's mass times its velocity, v1, and you add it to the other object's mass times its velocity, so this object's momentum plus the other object's momentum before the collision. That'll be the total momentum after the collision. So let's go back and see if that's actually true. Let's reset it. Let's look at some values. This is an elastic collision, so its velocity is 1, its mass is 0.5, and I'm going to hit play. And this one's, we're going to add 0 to it, so its momentum is 0.5, its momentum is 0, so the momentum after should also be 0. Sorry, 0.5. This is negative 0.25, this is 0.75, and so the total momentum is 0.5. You take 0.75, negative 0.25, add them together, you get 0.5. This will hold true for no matter what we do. I'm going to reset it all. What if we made this object really, really large? Hit play. Let's see, look at values here. 2.4 and 0, so the momentum afterwards should be 2.4. Boom. Well, 1.85, 0.55, that adds up to 2.4. Indeed it does. This ball took off a lot, really small. It was smaller, so it took off with higher velocity. This one slowed down. It was moving 1 meter per second, now it's moving 0.23. So that's an elastic collision. Inelastic has a similar equation to it. Before I jump back to that, let's think of what's the equation for that. Well, you have 0.5 momentum before. You still have 0.5 momentum afterwards, but so 0.38, 0.13, it's rounded to 0.5 here. But the equation, there's something we can do with the equation here. In inelastic collision, we can take the object's mass times its velocity plus the other object's mass times its velocity, and then what does it equal? Well, since they're stuck together, we can add those two masses together, and then it'll equal some third velocity. And these have to match before and after. They have to match